CSIR Mark1 was really Australia's first foray into computing. Designed by Trevor Pearcey and engineered by Maston Beard, it became operational in 1949, being only the fourth or perhaps the fifth digital computer in the world to execute a program from memory. Amazingly, the CSIR Mark1 was made here in Australia in isolation from the rest of the world. When it was moved from Sydney to Melbourne, later in the 1950s, it became known as CSIRAC, the Commonwealth Scientific and Industrial Research Automatic Computer. As far as we know, it's perhaps the only first-generation computer still completely intact, all the others having been dismantled, many because they were actually secret machines being used for wartime operations.
The first calculator was really the fingers.
Late 40s and early 50s, a computer was a person sitting at a calculator.
And they had teams of girls who just worked calculating machines.
And the computing department was just rows of desks of people sitting at calculators, churning through these calculations that were required for modern physics.
There they needed, as far as possible, good, reliable calculations.
Of course, the military drove a lot of this for the trajectory of shells and all of those sorts of things, but also all sorts of engineering required these calculations.
I was using the techniques of the time for mathematical calculations, which included using book of tables, using a marchant calculator, and even using one of these things, which is a cylindrical slide rule. But the one calculation took me about 6 or 8, 9 months.
Calculations of incredible complexity, which would take you ages and ages and ages if you're just working your way through with pen and paper.
The weather is, as you know, a chaotic phenomenon, and it's very difficult to predict. The mathematical interpretation of the weather was something that was too difficult and too time-consuming to be done in a real-time process, even with the best mathematical minds around. And the best mathematical minds around would not become meteorologists, they would become mathematicians.
In the years leading up to the Second World War, massive calculators were built,
which could do very complicated calculations.
There were very complex tabulating machines, which the equipment from the tabulating companies was applicable to be used in a digital computer.
But these were very limited because once you'd programmed them, that's all you could do. You couldn't have any decision making by the program depending on the data it was processing.
The idea that you could have a computer that stored both memory and data meant that the commands in the computer and the data in the computer were treated essentially as the same thing, so that one could modify the command in the computer the way one modified data in the computer.
The great virtue, the great benefit of machines like CSIRAC was that they had within them, within their programs, the ability to make decisions about the data as it was being processed. CSIRAC came about because it was part of a general development across the world because there was a need for high-speed computation.
Well, CSIRAC was a huge advance over the calculating machines, which was all they had.
CSIRAC was a great Australian achievement very early, but I've met both Maston Beard and Trevor Pearcey, who worked and essentially designed CSIRAC. I wouldn't say that we had any intimacy, but I very much admired what they were doing.
I find Trevor Pearcey's work very interesting because he is very well known for his CSIRAC research and logic work. As a mathematician, he applied his knowledge to some very interesting different fields.
Trevor Pearcey was a remarkable person.
I've been looking at the aspects of Trevor Pearcey's career right from the beginning of his work in England.
Trevor Pearcey had experience with radar technology.
I was involved in the development of radar, particularly the mathematical aspects.
He was born in England and was a student in London, but then he graduated in 1940, and of course, like a lot of young physicists, he was taken into the military research area quite quickly.
I worked with Douglas Hartree on some of the computations of radar.
Who was the scientific advisor for the government. He had high-level security clearance, but it was really radar work, which was all secret. That was the major development in England at that time for the defence of the country.
Radar technology was very important for the development of early computers because of the pulse technology that was involved.
The thing about computing is that digital computing didn't just appear.
Well, the war came along They needed to decode German radio transmissions and stuff like that, which were all coded. So Turing worked out a mechanism for handling that. And the first thing he built was a machine called the bomb, which allowed that to be done electromechanically. The second thing he didn't build, but he kind of worked out all those processes for Colossus, which essentially a parallel pattern processing machine, i.e. they are a fixed algorithm computer.
Meanwhile, Trevor Pearcey transferred to the country to Malvern, and he was at a place called Pale Manor. There were 4,000 people at Malvern.
The arrival of radar meant that one had to generate short pulses, send them out, receive them, amplify them, display them. That brought in a whole raft of quite detailed issues, particularly when you've got large electronic components with delays in them. And so pulse shaping and synchronizing pulses so that one pulse gates another pulse was very important in terms of display technology and so on for radar.
And various problems to improve radar, to put it into planes, so they had mobile radar, and they wanted to defend the shoreline of the country. It was secret work. They couldn't reveal what they were doing. They worked 6.5 days a week. It was an enormous work effort and work ethic. Trevor was working on radio wave propagation. He did a significant amount of his calculations on the differential analyzer at the Manchester University.
And a corresponding differential analyzer at the University of Cambridge. I was involved in running the same problem on both of these machines concurrently.
This was probably the first time he came across mechanical computing. Differential analyzers were analogue machines. They had moving parts. And in fact, Douglas Hartree had seen one in the US and famously came back to Manchester and built one out of Meccano.
We also had a linear equation solver called the Malloc machine. We used punch card systems for tabulation of mathematical functions.
This notion that you could take an algorithm and mechanize it is, in a sense, the basis of computing.
During World War II, radar engineers started working with mercury baths to try and cancel out the radar echoes. It wasn't a large step from there to think about storing information as pulses in a mercury acoustic delay line, which would recirculate. So you put a pulse in, it gets to the other end, it gets recirculated, and then you can fit so many pulses into a length of tubing. And the idea of storing information in liquid metal was just so bizarre.
People then also were using cathode ray tubes as a memory storage device.
It's when a man called Freddie Williams sat down and realised with a CRT is that it actually, for a moment, it stores, it holds and continues to generate electrons off the faceplate. And you could store that. That allowed you to place dots of phosphor brightness on a surface. So it now had not only the acoustic delay line, the mercury tube full of memory, you had this cathode ray tube type of memory. In the process, they produced the first bitmap graphic. And it's the use of that which allowed the Manchester University people, under a man called Max Newman, to produce the first stored program computer.
So memory is this key factor in these different early machines.
And so computers were developed, what we know as a computer today, which at the time was called an automatic computer. These machines were developed to automate that process so that we could more quickly calculate.
Have an idea that Hartree is the grey eminence behind all the first computers, well, certainly the first 3 computers.
He probably, I think, would have known about the work at Bletchley Park. And most people now know about the work at Bletchley, but the people at the time, they weren't aware of the computers being developed. It was extremely secretive, and it was secretive post-war. I mean, the reason a lot of the code-breaking equipment kept in use, so it was not discussed.
The people who came out of that Bletchley Park decryption group became the computer pioneers for the next generation.
No one knew what anyone else was working on, and they wouldn't have met these people.
At the end of the war, they pulled them all apart, put the parts all back on the shelves. Now, these are all vacuum tube machines.
After the war, both Manchester and National Physical Laboratory wrote to the Royal Society of London and asked for funding to build a computer. And the Royal Society of London wrote to Hartree and asked him to advise which one they should support. And he said both.
He was a major advisor and authority for them on computing. He would have known so many different things, but he could not pass on ideas to people. I just wonder if he made suggestions to lead them in that way, but it's hard to know. He could not reveal a secret, and he obviously did not reveal secrets.
Hartree was the person who recommended both the Manchester machine, the ACE, and mentored Pearcey.
He is a continual element in Trevor Pearcey's work.
In Australia during that wartime period, one of the most important developments that took place was at CSIR Radiophysics, where they developed the distance measuring equipment. What DME did was that it got radiophysics interested in electronics at that level.
Right at the beginning of 1945, the war was winding down. There was thousands of young scientists having to make a decision. What would they do next? Trevor Pearcey came to Australia via the US.
And seen some of the calculating machines and early computers in America.
Including mechanical or electromechanical machines, and realised they weren't fast enough.
Ideas for CSIRAC really stemmed from a visit to Howard Aiken at Harvard.
What that involved, that he had access to, was the Harvard Mark1.
This was a huge machine built largely from IBM counter components and ran, I think, 24-hole paper tape for its program and input data. It was clear that whilst this operated at 2 operations a second, in the future we would need at least a 100-fold increase in speed. This meant that we would have to go to electronics.
Trevor Pearcey applied for the job. They advertised in England.
And I arrived in Brisbane on a Skymaster US Army transport aircraft on Boxing Day of 1945.
And joined the CSIR Council for Scientific and Industrial Research.
And he went to radiophysics.
He was recruited from the UK by Taffy Bowen after World War II, and he had the knowledge, contacts with people overseas who were working on the ideas of digital computers, so he brought that to Australia.
I don't think he would have known that the CSIRO was particularly going to support computing. After all, they didn't know what it was.
Radar expertise here was very, very good. In World War II, Australia had developed portable radar systems for our soldiers to take into the field in jungle warfare, and that was fairly extraordinary in its day.
Radiophysics was a leading place in the world in radar design. In fact, there are claims that radar that arrived from Britain was not suitable for tropical and other conditions in Australia. Radiophysics sorted it out, and they were really an outstanding example of our local capability.
When he arrived, he said, there's a lot of work here. Mechanical computing would be the way to solve our workload.
During 1946, I began to develop ideas for an electronic system for computation using a notation developed by Pitts and McCulloch.
Warren McCulloch and Pitts in 1943 produced a paper. It's a psychological paper talking about how brain works and the logic of thinking and completing a problem. John von Neumann quotes this paper in his June 1945 paper for the logic for ENIAC. That paper was very limited circulation, but I think the really interesting thing is that that paper later Trevor quotes as being his inspiration for the logic. It's a very obscure paper. Hartree certainly did know about the logic, and this paper by McCulloch and Pitts, it really is quite a significant thing that in 1984, that's what Trevor Pearcey quoted as a significant influence on his thinking, because to know about that paper, I'm sure the only reason he would have known about it was that either Hartree or Comrie gave it to him to read.
We discussed various aspects of computing, and it is with him that I learnt most of my mathematics of numerical methods and practical aspects of solving differential equations.
And he persuaded the people at Radiophysics in Sydney that they should build a computer.
I mean, it's a £50,000 project he sells them on, so he must have had something to suggest as possible.
Towards the end of 1947, I had more or less completed a theoretical logical design for what was to become CSIRAC.
If you were working with that sort of ideas and equipment, you knew the potential of something that could be applied somewhere else. And I think that's the thing about innovation. You connect up different ideas and put them together to make a functioning item that can do the logic work, but can also do the mechanical, electronic activities that are necessary.
I was not aware at that stage of work that had already been carried out, the highly theoretical work of Kurt Gödel or Alan Turing. So we started off designing CSIRAC ab initio.
By 1947, they were up at places like Manchester University and Cambridge University and so on, and they were building, and Turing had gone to what was known as the National Physical Laboratory, and each of these groups were trying to build real electronic computers.
In June 1948, the baby at Manchester ran the first store program, Kilburn and Williams. Previous machines have been not store program. Some of them were programmable in a sense, but not store program, or they were not electronic.
I was not aware of developments other than the differential analyzer at MIT and the Harvard. Later knowledge came to us of the Bell developments of relay machines. During 1948, we heard of the development of the EDVAC by Wilkes.
EDSAC came online in mid-1949, probably the first real computer that did a job of work, as far as one can tell, rather than was an experimental engineering thing.
And the other place was the National Physical Laboratory, which was building the ACE.
But then before that, there was all the business of ENIAC and Colossus.
Although I did not see ENIAC or hear of it at the time, during 1945 and 1946, I think it transpires that ENIAC is a glorified electronic calculator.
Certainly the Colossus developers and so on, and the people who reconstructed said no, it was not a programmable machine in the sense as we know it today. BINAC was meanwhile under contract. They were building it in the States for Northrop, I think. Now BINAC was effectively rejected by the client, but it must have at least run a test program. So it must have been in early 49.
Meanwhile, the Americans are starting to control their borders in the sky electronically because they needed to know whether somebody was throwing missiles at them. They built a system called Whirlwind, which became SAGE.
Our own designs were essentially completely separate from developments of electronic computation.
CSIRAC was a development from the CSIRA Division of Radio Physics.
And he teamed up with a very good electronics engineer by the name of Maston Beard. Together they designed and ultimately built one of the world's first computers.
Maston Beard, who became the design engineer, developed all the electronics within CSIRAC, had worked on radar in radio physics during World War II.
He was not loquacious, a man of few words, I think we'd say, quite bad.
There were only 4 or 5 of us, Maston Beard, Reg Ryan, Brian Cooper, the draftsman programming team, which consisted of myself and Geoffrey Hill.
The logic was, and his overall vision was, pushed a lot of other people along to create the parts of the machine that would then answer these questions.
I did travel to the UK in November and December 1948 after I had completed the logical design of what became CSIRAC. Although we studied the circuitry, very little of the actual design of EDSAC and its circuitry, which was completely based on UK vacuum tubes, which were quite different from the US type vacuum tubes which were available in Australia through AWA. So very little of the actual techniques of EDSAC were incorporated later by Beard in the completion of CSIRAC.
I think it's unlikely that the whole thing came fully formed out of Trevor's head and they just built it. I think it was, let's do something which can execute instructions, and new ideas came.
Maston Beard had already started developing some of the electronic circuitry for it, while Trevor was thinking about the software side, the mathematical side of it.
Well, if it hadn't been for Maston Beard and myself, CSIRAC would never have been conceived or constructed.
CSIRAC was essentially an Australian innovation.
One of the interesting components in this, of course, is the role of Reg Ryan, who actually built the memory.
It was decided that I should work on the mercury delay line memory.
My theory about Reg Ryan was that they didn't tell him that it hadn't been done before. And he was a young engineer, so he just went ahead and did it, you know. He thought up a way of interleaving the pulses in the mercury delay line, so he doubled the capacity.
The construction of CSIRAC, which was essentially an experimental prototype machine.
In Sydney, where it was first developed, was an experimental device where they were basically developing it in order to see whether they could produce such a machine.
This is the extraordinary thing about this machine, that it was, I think, part proof of concept, but part a useful tool.
While I was concerned with the logical design up to the detail of gates and registers and transfers of digits and so on, Maston was responsible for the entire electronic development and the mechanical development of the peripheral equipment, and I tried to keep myself out of the engineering work so that he would have a completely free hand.
At the time when they built it, they could have just... I've heard some early machines described as spaghetti. The wiring is just everywhere. But CSIRAC was built by engineers who had a pride in what they were doing.
The physical construction seemed to go fairly smoothly. Of course, Radiophysics Division had a very experienced and extremely well-equipped workshop for wiring up the major components and for building the boxes and the frames.
CSIRAC has the greatest Australian content of any computer ever made.
We could make our own contribution and come up with hopefully an improved one, or one which would, I think inevitably would be different from the others, since we weren't just taking a design that existed overseas. We were taking the concepts, and Trevor Pearcey and Maston Beard developed the concepts, and then we developed the hardware. I developed the mercury delay line and introduced the interspacing, which I don't think people did overseas, to increase the memory capacity.
I think it was towards the end of 1949, CSIRAC was sufficiently developed to run a rudimentary program.
I don't think it was a big celebration, champagnes or anything like that. Yeah.
The first test program, which was a 20 by 20 digit multiplication, was of course designed by myself. I think I had to go through the setting of the keys on a lash-up switchboard for putting these instructions bit by bit and word by word into the delay line store, and then starting the program, and then viewing the progress of the digit by digit multiplication on monitor cathode ray tubes. We were thrilled when it worked.
It must have been exciting. I would have liked to have been there, actually.